Have you ever wondered about the math behind repeating patterns or how images are flipped and rotated in designs? The answer lies in geometric transformations, mathematical operations that move, flip, turn, and resize shapes in precise, predictable ways. These transformations are everywhere around us. In nature, we see perfect reflections creating symmetrical patterns like butterfly wings. In architecture and engineering, rotations help us understand how gears turn and wheels spin. In video games and computer graphics, translations move characters smoothly across the screen. Understanding these four fundamental transformations translation, reflection, rotation, and dilation gives us the power to describe and predict how shapes behave in our mathematical and digital worlds. Geometric transformations are fundamental mathematical functions that change the position, size, or shape of figures on a coordinate plane. Think of them as precise mathematical rules that tell us how to move or modify geometric objects. These transformations work by taking every point in a geometric figure and moving it to a new location according to specific mathematical rules. The original figure is called the pre-image, and the result is called the image. There are four main types of geometric transformations. Translation slides a figure from one location to another without changing its size or shape. Reflection flips a figure over a line to create a mirror image. Rotation turns a figure around a fixed point by a specific angle. And dilation resizes a figure proportionally, making it larger or smaller while maintaining its shape. These four transformations are the building blocks for more complex geometric operations. Understanding geometric transformations is crucial in many fields. Computer graphics use these transformations to create animations and 3D models. Architects and engineers apply them in design and construction. Even artists use transformation principles to create symmetry and visual effects. In the following sections, we'll explore each transformation type in detail, learning how to identify them, apply them step by step, and solve problems involving geometric transformations on the coordinate plane. A translation is one of the most intuitive geometric transformations. Think of it as sliding a figure from one location to another, like moving a piece on a chessboard or sliding a book across a table. A translation is a transformation that slides every point of a figure the same distance in the same direction. The key word here is same. Every single point moves by exactly the same amount. Translations have three crucial properties that make them special. First, the size of the figure never changes. Second, the shape remains identical. Third, the orientation or direction the figure faces stays exactly the same. Here's a triangle on our coordinate plane. Watch what happens when we translate it. Notice how every point of the triangle moves by exactly the same amount in the same direction. The triangle slides from its original position to a new location. Every vertex moves 4 units right and 1 unit up. The triangle maintains its exact size, shape, and orientation throughout the movement. To describe a translation precisely, we use something called a translation vector. This vector tells us exactly how far to move in the horizontal direction, called the x direction, and how far to move in the vertical direction, called the y direction. Here's our specific example. We start with point 2, 3, and we want to translate it using the vector 4 minus 1. The vector tells us to move 4 units to the right and 1 unit down. This orange arrow represents our translation vector. It shows both the direction and distance of the movement. The arrow starts at our original point and points to where the point will end up. The mathematical calculation is straightforward. We add the translation vector to our original point coordinates. 2 plus 4 equals 6 for the x-coordinate. 3 plus -1 equals 2 for the y-coordinate. So our new point is 6, 2. Now watch as the point slides along the translation vector to its new position. The point moves smoothly from 2, 3 to 6, 2, following the exact path shown by our orange arrow. Here's the general formula for translations. To find the new position x prime, y prime, we add the translation vector components to the original coordinates. This simple addition gives us the exact location after the translation. Remember, translations preserve everything about a figure except its position. The size, shape, and orientation remain unchanged. This makes translations one of the most predictable and useful geometric transformations. Now we explore reflections, one of the most intuitive geometric transformations. A reflection creates a perfect mirror image of a figure by flipping it over a line. A reflection is a transformation that flips a figure over a line called the line of reflection. Think of it like looking in a mirror. Every point on the original figure has a corresponding point on the reflected image, equidistant from the line of reflection. The line of reflection acts like a mirror. When we reflect our triangle over the y-axis, each point moves to the opposite side of the line, maintaining the same distance from the line of reflection. Notice how the reflected image is congruent to the original, same size and shape, but its orientation has changed. This is a key property of reflections. Let's examine the three most common types of reflections, starting with reflection over the x-axis. When we reflect a point over the x-axis, the x-coordinate stays the same, but the y-coordinate changes sign. Let's see this in action. We'll reflect the point 2, 3 over the x-axis. According to our rule, this becomes 2, -3. Notice that both points are exactly 3 units away from the x-axis, but on opposite sides. This equal distance property is fundamental to all reflections. Next, let's examine reflection over the y-axis. Here, the y-coordinate remains unchanged, while the x-coordinate changes sign. Let's apply this rule to the point 4, 2. Reflecting over the y-axis gives us -4, 2. Again, we see that both points are equidistant from the line of reflection, in this case, 4 units from the y-axis. The third common reflection is over the line y equals x. This diagonal line creates a unique transformation where the x and y coordinates swap places. Let's demonstrate with the point 3, 4. When reflected over the line y equals x, this point becomes 4, 3. The coordinates have simply switched places. This reflection over y equals x is particularly useful in mathematics because it represents the inverse relationship between x and y coordinates. A crucial property of reflections is that they change the orientation of figures. Unlike translations and rotations, reflections create a mirror image that cannot be rotated to match the original. This orientation change is what makes reflections unique among geometric transformations. It's why your reflection in a mirror appears backwards. The image has been flipped, changing its orientation relative to the original. Understanding reflections and how they transform coordinates is essential for mastering geometric transformations. Remember the 3 key rules. Over the x-axis changes y to -y, over the y-axis changes x to -x, and over y equals x swaps the coordinates. Now we explore rotations, one of the most dynamic geometric transformations. A rotation turns a figure around a fixed point, creating smooth circular motion while preserving the shape and size of the original figure. Every rotation is defined by exactly 3 components. First, we need a center of rotation. This is the fixed point around which everything turns. Second, we specify the angle of rotation, how many degrees to turn. Third, we choose the direction, either clockwise or counterclockwise. We'll demonstrate rotations using the coordinate plane. Here's our center of rotation at the origin, and we'll rotate this blue point P at coordinates 2, 0 around the origin. Watch as we rotate point P by 90 degrees counterclockwise around the origin. Notice how the point follows a circular path, maintaining its distance from the center of rotation. As the point rotates, watch how its coordinates change smoothly. The x-coordinate decreases while the y-coordinate increases, following the circular motion. Now let's examine the most common rotation angles and see how coordinates change with each rotation. We'll start with the same point at coordinates 2, 0. For a 90-degree counterclockwise rotation, our point at 2, 0 moves to 0, 2. Notice how the x and y coordinates essentially swap, with the original x-coordinate becoming the negative of the new y-coordinate. For a 180-degree rotation, the point moves to -2, 0. Both coordinates change sign. This is like reflecting through the origin. For a 270-degree rotation, which is the same as -90 degrees, our point ends up at 0, -2. This completes 3/4 of a full rotation around the origin. Here are the general rules for rotating points around the origin. For 90 degrees counterclockwise, x becomes -y and y becomes x. For 180 degrees, both coordinates change sign. for 270 degrees, x becomes y and y becomes negative x. The key insight is that the distance from the center always remains constant. Finally, let's see how rotation works with a complete figure. Here's a triangle with vertices at A10, B21, and C12. We'll rotate this entire triangle 90 degrees counterclockwise around the origin. Applying our rotation rule to each vertex, A at 10 becomes A prime at 0, 1. B at 2, 1 becomes B prime at -1, 2. C becomes C prime at -2, 1. The entire triangle rotates as a rigid body, maintaining its shape and size. Rotations are rigid transformations that preserve the shape, size, distances, and angles of figures. Remember that every rotation needs three pieces of information: the center of rotation, the angle of rotation, and the direction. With these tools, you can rotate any figure around any point in the coordinate plane. Now we explore dilations, a unique type of geometric transformation that changes the size of figures while preserving their shape. Unlike translations, reflections, and rotations, dilations are non-rigid transformations. A dilation is a transformation that resizes a figure proportionally in all directions from a fixed center point. This means every part of the figure gets larger or smaller by the same ratio. There are two key concepts in dilations. First, the scale factor, represented by k, determines how much the figure is resized. Second, the center of dilation is the fixed point from which the resizing occurs. When k is greater than 1, we get an enlargement. When k is less than 1, we get a reduction. Let's examine how dilations work on a coordinate plane. We'll start with dilations from the origin, which is the most common center of dilation. The origin serves as our center of dilation. All points will be resized relative to this fixed center point. Consider the point at coordinates 2, 3. We'll dilate this point using a scale factor of 2. The rule for dilation from the origin is simple. Each coordinate is multiplied by the scale factor k, so the point xy becomes kx, ky. With a scale factor of 2, we multiply each coordinate by 2, so 2 times 2 equals 4, and 3 times 2 equals 6. Our new point is at 4, 6. Here's our dilated point at 4, 6. Notice that both points lie on the same line through the origin. This is a key property of dilations. Points, their images, and the center of dilation are always collinear. We can verify our dilation by checking distances. The original point is about 3.6 units from the origin, while the dilated point is about 7.2 units away. The ratio is exactly 2, confirming our scale factor. Now let's see how dilation works with a more complex figure. We'll dilate an entire triangle using the same scale factor of 2. Here's our original triangle with vertices at A11, B31, and C23. We apply the scale factor of 2 to each vertex. A at 11 becomes A prime at 22, B at 31 becomes B prime at 62, C at 23 becomes C prime at 46. Here's our dilated triangle. Notice how it's exactly twice as large as the original, but maintains the same shape. The angles remain unchanged, and all sides are proportionally larger. Dilations have several important properties. The shape is always preserved, creating similar figures. All angles remain exactly the same. Every length is scaled by the factor k, and importantly, the area is scaled by k squared. Dilations can also make figures smaller. When the scale factor is between 0 and 1, we get a reduction rather than an enlargement. Here we have a square with side length 4 units. When we apply a scale factor of 1.5, each coordinate is multiplied by 1/2, creating a smaller square with side length 2 units. To summarize, dilations are transformations that resize figures proportionally while preserving their shape. The scale factor determines whether we get an enlargement or reduction, but the angles and overall shape always remain the same. This makes dilated figures similar to their originals. Now we'll work through 3 guided examples to apply what we've learned about geometric transformations. Our first example focuses on translation, the simplest transformation. Here's our problem. We have triangle ABC with vertices at A12, B42, and C25. We need to translate this triangle by the vector 3 minus 2. What will be the coordinates of the new triangle A prime, B prime, C prime? First, let's visualize our original triangle on the coordinate plane. I'll plot the 3 vertices and connect them to form triangle ABC. Now I'll show the translation vector. This vector tells us to move 3 units right and 2 units down. Remember, translation means every point moves the same distance in the same direction. To find the new coordinates, we add the translation vector to each original vertex. For point A prime equals 1 plus 3, 2 plus negative 2, which gives us 4, 0. Similarly, for point B prime equals 4 plus 3, 2 plus negative 2, giving us 7, 0. And for point C prime equals 2 plus 3, 5 plus negative 2, which is 5, 3. Now let's see the transformation in action. Watch as triangle ABC slides to its new position to become triangle A prime, B prime, C prime. Notice how the shape and size remain exactly the same, only the position changes. Perfect. The translation is complete. A common mistake students make is forgetting to apply the translation to all vertices, or mixing up the signs in the vector components. Always double-check that you're adding the vector components correctly to each coordinate. Our second example involves a composition of transformations, applying multiple transformations in sequence. This is where things get more interesting, and we need to be very careful about the order of operations. Here's our problem. We have square PQRS with vertices P11, Q31, R33, and S13. First, we'll reflect it over the y-axis, then rotate the result 90 degrees clockwise about the origin. What are the final coordinates? Let's start by plotting our original square. Notice it's positioned in the first quadrant, which will make the transformations easier to visualize. Step 1, reflection over the y-axis. When we reflect over the y-axis, the x-coordinate changes sign while the y-coordinate stays the same. So P of 1 becomes P prime negative 1, Q3 becomes Q prime 1, and so on. Step 2, now we rotate 90 degrees clockwise about the origin. For clockwise rotation, the rule is xy becomes y negative x. This is a critical point where students often make mistakes. Remember, it's clockwise, not counterclockwise. Let's see the final transformation. The square rotates 90 degrees clockwise from its reflected position. Notice how the composition of these two transformations has moved our square to a completely different location and orientation. A crucial point about compositions: order matters. If we had rotated first and then reflected, we would get a different result. Always perform transformations in the exact order specified in the problem. Our final example combines dilation with translation. This is the most complex type of transformation composition because dilation changes the size of the figure, which affects how we think about subsequent transformations. Here's our challenge problem. Rectangle ABCD has vertices A24, B64, C68, and D28. First, we'll dilate it by a scale factor of 0.5 centered at the origin. Then we'll translate the result by the vector 1 minus 2. Find the final coordinates. Let's visualize our original rectangle. It's a 4 by 4 square positioned in the first quadrant, which will make it easy to see the effects of our transformations. Step 1, dilation by scale factor 0.5. When we dilate from the origin, we multiply each coordinate by the scale factor. Since 0.5 is less than 1, our rectangle will shrink to half its original size. Step 2, translation by vector 1 minus 2. Now we add 1 to each x-coordinate and subtract 2 from each y-coordinate. This moves our smaller rectangle 1 unit right and 2 units down. Here's our final result. The rectangle has been shrunk to half its original size and moved to a new position. Notice that the final rectangle is a 2 by 2 square, exactly half the dimensions of our original 4 by 4 rectangle. Key insight: when combining dilation with other transformations, the dilation affects the entire figure uniformly. A common mistake is forgetting that dilation changes distances. So if you measure lengths or areas after dilation, they will be different from the original figure. We've covered a lot of ground in our exploration of geometric transformations. These 4 fundamental operations, translation, reflection, rotation, and dilation, are the building blocks for understanding how shapes move and change in the coordinate plane. Let's quickly review each transformation type. Translation slides a figure from one location to another without changing its size or shape. Every point moves the same distance in the same direction. Reflection creates a mirror image of a figure across a line of reflection. The original and reflected figures are congruent, but have opposite orientations. Rotation turns a figure around a fixed center point by a specific angle. The shape and size remain unchanged, but the orientation changes based on the angle of rotation. Dilation resizes a figure proportionally from a center point using a scale factor. Unlike the other transformations, dilation can change the size of the figure while preserving its shape. This brings us to a crucial distinction. Translation, reflection, and rotation are rigid transformations. They preserve both the shape and size of figures, creating congruent images. Dilation, on the other hand, is a non-rigid transformation. It preserves the shape of figures, but changes their size, creating similar rather than congruent images. Understanding these transformations opens doors to many areas of mathematics and real-world applications, from computer graphics and architecture to art and engineering design. If you found this video helpful, please give it a like and subscribe to our channel for more mathematics content. Leave a comment below if you have questions about geometric transformations or suggestions for future topics you'd like us to cover. Continue building your mathematical foundation by watching our next video on coordinate geometry, where we'll explore how to work with points, lines, and shapes in the coordinate plane. Thank you for learning with us, and we'll see you in the next video.